Thank you all for joining us today. My name is Kristen Rosa. I'm the marketing director here at Sunset Learning Institute. And today we're excited to be joined by our friends and co-sponsors CWNP, who will be covering wireless and the Internet of Things, learn the important facts from Wi-Fi to IoT-specific protocols. So for those of you who aren't familiar, CWNP offers enterprise wireless certifications for entry-level professionals all the way up to seasoned network experts. These certification levels are designed to benchmark your understanding of RF technologies and applications of wireless networks. So Sunset Learning is an authorized CWNP learning partner, and we offer the official training associated with those certifications. Your presenter today is Tom Carpenter. Tom is the CTO of CWNP, and he's a CWNE and CWISE. He's been involved in wireless projects since the early 2000s and brings a wealth of knowledge and experience to not just wireless, but any IT topic. So I believe Tom is going to kick it off with a quick poll question to kind of gauge the audience, see who we have here today, and then the presentation will begin after that. So Tom, over to you.
Absolutely. And so we do have a poll just to find out a little bit about those in attendance today. And it's asking, what industry are you in? Because as I'm talking about wireless IoT, it would probably be useful for any examples I talk about to make them as applicable to you as possible. So if you'll quickly fill out that survey, I'm going to go ahead while you're doing that and just kind of give you an overview from a high level of what we're going to talk about today. So first of all, we're going to talk about what IoT actually is. There are a myriad of definitions. People define it in different ways. So I'll share with you CWNP's definition of wireless IoT and IoT in general, for that matter, so that you'll understand our perspective and where we're coming from with this topic. And then we'll talk about some IoT use cases for different industries and get an understanding for how it might be applied. We'll talk about IoT protocols specifically and discuss the various protocols that are out there, Wi-Fi, but also non-Wi-Fi protocols. And then I'll share with you some concepts related to planning and designing a wireless IoT solution. So we're going to look at the wireless IoT design framework that we provide at CWNP, which gives you a map that you can use as your guideline for all of the parts and pieces, the components that have to be planned to effectively build a IoT solution that will give you the results that you need. While the framework, of course, is not going to cover every niche scenario, it's going to give you the fundamentals that are there in every scenario. And then there'll be some things that are unique in some cases that you have to deal with as well, but it will give you a solid foundation to build on. And we'll talk about a couple of examples of important things related to issues like quality of service and security within that framework. And then we'll wrap up with questions and answers at the end. So what I'm seeing is it looks like many of you are from other industries other than government, industrial, manufacturing, retail, oil and gas, and business or office. But we do have some from industrial manufacturing and some from business and office. I notice some mentioning education. And for the perspective of wireless IoT, the good news is that the protocols work the way they work, regardless of the industry that I'm in. And what I need to do is understand my building structure. If I'm outdoor, the terrain, for example, am I in a mine? Am I in a forest? Am I in an open area? All of these will impact the functionality and propagation of the wireless signals. And so it's very important to know about that environment. And we do have some consistencies within different environment types. So for example, one mentioned being in education. And the reality is that there are some consistencies in education, meaning that you've got buildings with lots of rooms and quite often with very thick walls in some cases, particularly older buildings, and issues that have to be addressed with any kind of wireless propagation. So when we're talking about wireless IoT, we have challenges that you do not have with wired IoT. But then again, when you're talking about wired IoT, you have challenges that you do not have with wireless IoT. Obviously, with wired, the challenge is getting the wire, the cable there. With wireless, the challenge is getting the radio frequency signal there. So both of them have their challenges. They are different, and they're overcome, obviously, in different ways. So we're going to move on then and begin our discussion of what IoT really is. So first of all, let's begin by understanding one of the big drivers of IoT over the last decade. IoT really became a common buzzword around 2010 to 2012. We saw an upward trend as it catapulted into popularity in the vernacular of the technology industry, as well as the industrial industry. And a lot of it was driven by this concept of Industry 4.0. So to understand this, we can look back at the history that led us to where we are today. And yes, that goes all the way back to the 19th century. And what we've seen is industry has driven a lot of our technological changes. Really, industry and government from different perspectives have driven a lot of our technological changes that have happened over the last century. And what happened was, first of all, we saw that at the beginning, we just had mechanical devices, machines that could do the labor of humans. And these machines usually required continual interaction with humans in order to do their work. But they took the work of a human and they allowed them to accomplish the same end result in factors of 10, 20, or even 100 times. And so they could produce much more quickly. And this was Industry 1.0, which really started just before the turn of the 19th century when the first mechanical loom was introduced. But then with Industry 2.0, we saw the assembly line. We saw automation of labor by moving things through an assembly line procedure. So rather than one person building an entire product, or even a few people in one area doing it, the product would move along to new locations and be modified or adjusted and enhanced until it reached the end of that assembly line and it was in its final state. So this was not just machines to do work, but machines or systems to move objects along for different machines and humans to do work. So this began to make a lot of changes. And it was really here where we started to see a lot of the resistance to these changes. And it's out of this era that we see the beginnings of the fear of technology, right? So as new technology comes along, there's concern over the loss of jobs and the inability of people to be able to be well occupied and have an income because of machines and automation taking their place. But what we saw out of Industry 2.0, while there was an early slump in the employment, we saw a great increase over a period of a decade or so, really a couple of decades in that time window that led up to what many of us have heard of the boom of the 1920s, right? And so we saw this great wealth and expansion of wealth and the ability of people to be well employed. But then along came Industry 3.0. And this is where we said, okay, instead of everything just being completely and purely mechanical, we have the ability to put some electrical logic in here. So we need to implement some systems that let us automate things even more. And this is where the modern PLCs, programmable logic controllers in industry come from. And many of what was done in manufacturing environments and industrial environments were eventually implemented on a micro scale in many cases to give us everything ranging from automatic thermostat control. Some of us are old enough to remember when you had to walk up to the thermostat and manually change the temperature anytime you wanted to change the temperature. But automation was introduced. And this was using some of the same type of electrical components that are used in the more advanced and fancy PLCs used in industry. And so we saw it spread throughout to be able to have automation in a lot of different areas and not just in the manufacturing environment. But notice what's happening here. It's getting more complex. First, it was just machines. Then it was machines with conveyor belts and assembly lines. Then it's machines with conveyor belts and assembly lines and electrical automation of the machines, the assembly lines, and so forth. And then that brings us to Industry 4.0, which many people will say launched around 2000 to 2010 timeframe. We'll say 2011 being the primary core of the launch of IoT. Now, that's not to say that IoT didn't exist before then. IoT was defined all the way back in the 1990s and a project related to Procter and Gamble. And so it's been around much longer than that, coined by Kevin Ashton as a term, really because he needed a good term to get the attention of executives. And at that time, the word internet in the late 90s was all the buzz, right? Before the internet bubble burst in the early 2000s. And so because of that, he just plugged in Internet of Things. He was planning on calling it Network of Things or Networked Things or something like that. But he realized to get attention, he needed that word internet in there. And hence the term or phrase Internet of Things was born. And by the way, that was an RFID project that he was dealing with at that point in time, radio frequency identification. And so with Industry 4.0, which we're still implementing at this point, right? We're dealing with IoT, robotics and AI, big data, cloud computing. And if you think about the last 10 years, what are the buzzwords? IoT, robotics, artificial intelligence, big data, cloud computing. These are all the buzzwords, and they're the driving force that Industry 4.0 has brought to us. But we're not done. Industry 5.0 is going to that next level. It's still robotics and AI, but it's more intelligent AI than what we have today. And we have seen some significant enhancements to AI in just the last decade. It has moved dramatically forward over what it was in the past. If we go back about 25 years ago to 35 years ago, we saw these systems called expert systems. They were all the craze with artificial intelligence. And today, those systems, people that work in the AI world would kind of laugh at them, saying that some would say they weren't even really AI. That's just how much artificial intelligence has evolved since that point in time. And so we have more advanced algorithms, more computing power, and a lot of other factors, such as massive amounts of data, that allow us to build better AI. So we're going to continue to see that intelligence increase because of what Industry 4.0 gave us. But if you think about it, that's nothing different than the past. Industry 1.0 gave us machines. So Industry 2.0 took that and added an assembly line. Industry 2.0 gave us machines and assembly lines, and Industry 3.0 took that and added to it the concept of automation with electronics. And then again, we saw that evolve with 4.0, and we'll see it with 5.0. But one of the big points of focus of Industry 5.0 is sustainability. You're going to see this being a huge, huge factor in the next decade, finding ways to implement technology and solutions in a sustainable and responsible manner. And we'll move on from this at this point, but I wanted to give you this idea of the background, because what this leads us to then is ultimately going all the way back to our mechanical loom. We want that loom to be connected. We want that loom to be able to talk on the network and to be able to be communicated with. And so that's what IoT gives to us. It gives us the ability to take these physical systems and make them cyber physical systems, make them connected physical systems so that they can communicate on the network, receiving information, sending information, and so forth. So that brings us then to the IoT and the definition of it. So what is IoT? Well, a common phrase that's used in relation to it is anything, anytime, any place. So the goal is to get any physical thing to be able to have connectivity at any time and from any location. Now, this obviously introduces challenges, but we've got solutions for most of these challenges. One of the challenges is, how do I get the network to where they are? Wireless is a good solution for that. And then, of course, anything, how do I get a physical thing connected? Well, it's just like us. How are we connected to the world? We're connected to the world through our eyes, through our ears, through our sense of touch, through our speech, right? So we communicate with our speech and with our bodies, We receive information through our visual systems, through our sense of smell, through our sense of hearing, through our sense of touch. We receive things. So you take any physical thing and then you give sensors to that thing. And those sensors allow that thing to communicate, to send information about it. Now, really, it's the sensors and the computing device monitoring the thing that send the information. But we like to think of it as a holistic physical thing. But the reality is there are things attached to it that sense the information and then send it across the network. So we do have solutions. But what is the definition? Well, the CWNP definition is that the Internet of Things is the interconnection of things, physical and virtual, mobile and stationary, using connectivity protocols and data transfer protocols that allow for monitoring, sensing, actuation, and interaction with and by the things at any time and at any location. One of the things I want you to notice about this definition is that other than the phrase Internet of Things, the word internet is not in here. So you'll see some definitions of IoT that say IoT is connecting things to the internet. But that's a very large oversimplification of what IoT has evolved into. And not only that, it's a modification of what IoT originally was based on its name in the 1990s. And so the reality is that IoT is just about interconnection. It doesn't have to be connected with the internet. It may be, or it may simply be connected to your local network. It can still be categorized as IoT if we're dealing with getting things connected to other things, to the network, or to humans. So this is a definition of IoT that encompasses what we have to deal with here. Now, what are we dealing with? Well, let's take a look. So when we deal with connections, IoT versus non-IoT, and these are connections to the internet, right? So these are devices connected to the internet. If you take a look all the way back at 2010, I said 2010 and 11 is that time frame when IoT began to explode, right? Well, look around 2010, you have 0.8 billions of connected IoT devices, but you have 8 billion non-IoT devices, you know, laptops, mobile phones, desktops, etc. Move forward 20 years to 2020, and what do you see? You see that IoT had passed non-IoT. More IoT devices connected than non-IoT devices. I'll give you one example. One retailer, for example, is deploying literally hundreds of millions of IoT devices, just that one retailer, over the next 3 to 5 years. And so when you begin to think of it in that way, given that that's one retailer and there are thousands of retailers around the world, though not all as large as that one, you begin to see how we can reach into these billions. The expectation is that by 2025, there'll be roughly 3 times as many IoT devices connected to the internet as non-IoT devices. So obviously there's a huge growth. And it's important to note that these numbers do not factor in the rapidity of implementation that came along because of COVID. So according to eSize 2021 State of IoT Adoption, 98% said that COVID-19 impacted their projects. 27% said it accelerated it. 31% said they increased investments. Only 21% said it slowed down development. And 26% said it led to cancellation. So we have a greater percentage either accelerating or investing more in it than those that ended up canceling or slowing it down. So we saw a shift toward an increase in the rate of IoT adoption because of COVID-19. And you can imagine this, you know, we have health sensing, we have capacity sensing, and I mean human capacity within a facility, these kinds of things. So it makes sense that we see this growth that's taking place. So the thing is that we're seeing IoT grow very rapidly, and our technicians need to be well trained to understand how to select the best IoT solutions and plan and implement those IoT solutions, as well as to support and administer them. And this is the whole reason that CWNP developed the CWISE or wireless IoT track within our certification portfolio. So what's it really all about? Well, it's about gaining business insights from IoT solutions. And so you have your applications that are based on your data that is derived from your devices. These IoT end devices can sense and then report information, which becomes our data. And that data can be distributed and structured so that it's meaningful to us. It may come in a very unstructured way, but it can be distributed and structured so that it's meaningful data. And then our applications can access it and represent that data to provide business intelligence. So this is one of the big drivers behind IoT, because particularly if we're just sensing, so we're just monitoring what's going on and we're not doing actuation, we're not taking action based on what we sense automatically, but rather we're getting this for reporting information. And this is a big part of IoT, is just sensing and gathering or harvesting this data so that we can use it for business insights and intelligent decisions. So this is one of the big drivers behind IoT. And the way we implement IoT for these business insights or for control, such as in industrial manufacturing and even in home automation, we can categorize it into two general categories: massive IoT and critical IoT. Now, it's not to say that critical is not massive, and it's not to say that nothing in massive is critical, but they're general views of what the IoT is focused on within these deployments. So we have our basic massive IoT, and then we have our critical IoT. And the general descriptions might be that massive IoT is lower cost, lower energy, smaller data volumes, but massive numbers of devices. So because it's not critical, we don't need to get information or sensed reports 10 times a second, right? But we may need a report once a minute, once every 10 minutes, once an hour, once a day, even in some cases. But we have thousands of these devices or tens of thousands. So it's massive, but it's not necessarily critical depending on the deployment type. And then with critical IoT, it's high reliable, very low latency, very high availability, and very high security. The data is sensitive, the data is time critical, these types of factors. So what are some examples? Well, smart building can be generalized into massive IoT, even though parts of it will be critical. There'll be components that are critical. For example, health environment monitoring within a building can obviously be critical. And so we want quick alerts or notifications or even actions related to the detection of human harmful elements within the airspace. But when it comes to other things like simply temperature monitoring or something of that sort, we probably aren't going to be dealing with it as critical of a factor. And then you have your logistics, tracking, fleet management, and you have smart farming and capillary networks. These are local networks that provide connectivity over short range wireless, and then they route through a cellular network. Okay, so you've got these local little capillary cells that are communicating through your network to the cellular network for a backhaul. And again, they could be using that technology, but be critical. But we see a lot of these, especially in research monitoring of environmental analysis and things like that, that are more in the massive IoT category. Then the critical IoT, obviously things like traffic safety and control, smart grid, industrial application and control where there are accident or health danger or even life-threatening issues that could come up, and remote healthcare. These are obviously very, very critical, both dealing with privacy issues as well as time-sensitive issues and so forth. And then, of course, we can take any of these and say that they're really a hybrid. Example of a hybrid might be a smart city where there is both critical and massive IoT concepts. And then smart vehicles would be another one. And then any of these for your particular project may be massive and critical. So it's not to say that all IoT networks are one or the other, but they are categories that we can use to think of and conceptualize what our deployment needs. In industrial IoT, just to give you some examples of some of the benefits, we can accomplish centralized analytics. So we're not having to worry about going to screens throughout a plant our manufacturing environment in order to find information, but it is centralized. New business opportunities, the data that we're harvesting can reveal to us new business opportunities, or the increased efficiency of manufacturing can allow us to manufacture different things at different times that we didn't have the time to do before, and so forth. Safer and more productive work so we can protect our employees, process and behavior monitoring, so we can really truly understand our processes instead of just relying on someone telling us what the process is. We can analyze and monitor the actual flow of a product through our manufacturing process. And then we can optimize that. And of course, all of this results in improved decision-making. IoT for connected vehicles, just very quickly. This allows us to have our vehicles connected within them. So intra-vehicle communications, where the different systems within the vehicle can intercommunicate, usually using wires in most vehicles, because why not, since we can build the vehicle and implement the wires, but it could be wireless as well. And then you also, though, have vehicle to infrastructure, usually across wireless, obviously, vehicle to vehicle. This could be simply sensing other vehicles or actual communications with other vehicles eventually. Vehicle to cloud, vehicle to pedestrian, again, probably sensing, but at some point in the future, we may see some integration with wearable IoT devices on humans related to vehicles as well, especially as we see more and more autonomous driving. And vehicle to everything. So just to have something as a general category, anything else the vehicle might need to communicate with. Intel estimates that a single truly fully autonomous vehicle, not assisted driving, will generate 4 terabytes of data every 90 minutes. Now, not all of that is sent across the network, but this is the data it's generating from its various sensors to be able to do the work that it's doing, which tells you, by the way, just how brilliant you are. You know, if you ever feel unintelligent around a computer, think about this fact. An autonomous vehicle, which is still not going to be as good as a human, not really, it will not be aware of all those other things in the environment that you're aware of unrelated to driving at the same time as driving. And yet you can drive and you generally don't have an accident. And so you are mentally processing the equivalent of more than 4 terabytes of data every 90 minutes. If just the essential information for a car to be autonomous is 4 terabytes of data, and you're taking in extra, you're probably taking in 3 to 4 times that amount of data every 90 minutes, processing it, analyzing it. You are brilliant. Be confident in that. We're learning more and more about just how brilliant humans are as we continue to advance artificial intelligence. So the goal of an IT architecture then is ultimately to take information from the perception layer to the application layer. So the perception layer is where the data comes in from the IoT end devices. It goes across the network so that our applications can use it, where we have business decisions, insights, and control. So in this process, the data starts at the IoT end device and is sent to the network. But the first thing we have to do then is take that data and collect it in some way. So we're going to harvest that data from these end devices. And then after we've harvested the data, we're going to store that data somewhere. Now, this data could be stored in just one place or possibly in many places. And then we're going to process the data for availability on appropriate systems, which may result in additional storage. That is to say, we may have an initial store and a distributed store. Or in some scenarios, you may have real-time processing and you don't actually store it at all. And the only real storage is in memory until it's done being processed. And then it's simply discarded if there's no need or desire to retain it. We have all kinds of systems that do that. Your washer and dryer, if it has intelligent processing, will analyze sensed information, make decisions. It's storing that information only in memory while it needs it, but it's not permanently storing it anywhere unless you have a cloud connected one, which is storing some information in the cloud. So we've had intelligent devices that do this processing of the data and then simply discard it. And you may have some data that never leaves the IoT end device in some cases because it doesn't need to. So it's all processed on the device and action is taken there. Again, you have to factor in what you need of that data and make sure that goes across the network and then is stored, possibly even distributed to multiple storage locations. And once we have our data in the right locations, we have APIs, application programming interfaces, that allow our applications to get into that data, get the information, process it, provide us with insights, and so forth. And so this is the overall structure of what IoT is trying to do for us, giving us this simplified model of 3 layers: the perception of what's going on with the cyber physical systems, that information going across the network. We're collecting, storing, processing, and accessing it to get our business insights. So what protocols do we actually use to get all this done? Well, there are quite a few protocols. So certainly we can use Wi-Fi. 802.11 is the formal name of Wi-Fi in the standards. We have 802.15.4, which is another standard created by the same organization, the IEEE, the Institute of Electrical and Electronics Engineers. And then 802.15.4 is actually the foundation for several other protocols. 6LoWPAN, which is listed here. ISA 111A, which is listed here. Wireless HART. Okay, these all use 802.15.4 under the hood. And so the reality is that 802.15.4 is a standard protocol, but very few IoT networks just really implement 802.15.4 alone. They tend to implement one of these other protocols that defines things above 802.15.4. So it gives you the ability to communicate at the lowest layers, but then it's the other protocols that define all the special ways in which communication happens for specific types of IoT solutions. For example, ISA 111A and Wireless HART were engineered specifically for industrial manufacturing type environments, whereas 6LoWPAN is a more general type of wireless IoT protocol. Then we also have Bluetooth, which is not 802.15.4, though some people do get confused and think that it is. It's developed by the Bluetooth Special Interest Group today, and it's gone through many versions. The versions best used for IoT are Bluetooth 5 and above, or BLE. And then we have some long-range protocols like LoRaWAN and Sigfox. These are designed to be very long-range protocols, up to 10 kilometers or more, depending on the scenario. Then we have Zigbee, which is one of the oldest protocols that IoT wasn't even commonly used as a term yet when Zigbee came along in the early 2000s. But then it obviously was used for IoT when IoT became the popular term. So if you really think about it, we were already doing IoT with Zigbee before we were commonly calling it IoT. So while we can say that IoT didn't explode until 2011, is really the term. These things we implemented called wireless sensor networks, going back to the 90s actually, and a little bit before that. Many of them would be categorized as IoT if we were building them today. That's just the reality, okay? So the important thing is to know the concept of IoT has been around for a while, and that's why we have so many protocols. Then we also have Z-Wave, which is mostly used in consumer, though it might be used in some small and medium businesses, even some larger businesses in office spaces and so forth. But it is not the common protocol used in industrial and manufacturing and that kind of thing for sure. Now, look at where these different protocols operate. Okay, so 2.4 gigahertz, that's the frequency of the radio frequency wave that is being produced. 2.4 is the most common that you see here. And then some are sub 1 gigahertz. They're down below 1 gigahertz. Now that's an important thing because this results in the 2.4 gigahertz band being congested because so many protocols work there. You've got 802.15.4, you've got Bluetooth Classic, your headphones and mice and keyboards and so forth. You've got BLE and 802.11. And this is just some of them, right, that operate there. And when I say you've got 802.15.4, remember, I mean ISA 111A, Wireless HART, etc. Different protocols by name may actually be using this and working in the 2.4 gigahertz band. So what does this mean? It means that we have to make absolutely sure that we're addressing the wireless communications that we're using in 2.4 gigahertz so that they can all live together. This is a fairly big challenge for many IoT deployments that don't want to use Wi-Fi, but they do want to use some other 2.4 gigahertz wireless IoT solution. And they've already got Wi-Fi used to some significant level of capacity already in that environment. So now either The Wi-Fi will interfere with the wireless IoT, or the wireless IoT will interfere with the Wi-Fi. We have to do strategic planning for channel utilization to try to keep them from stepping on each other. We're not going to get into the details of that here, but it's a very important thing to keep in mind. Now, I do want to show you one thing to help you understand why the selection of a wireless IoT protocol is important. What I'm about to show you could be explained in an extremely technical manner. I'm going to keep it at a basic graphical level and use simple terminology just to make sure everybody here today will comprehend it, regardless of your level of training in RF engineering. So when you are communicating on a wireless network, the information you want to send, and remember, for computers, all information is ones and zeros, right? It's what it ultimately is. And so when you're sending those ones and zeros, we have to have a way to represent a 1 and a 0 on the wireless signal. And we accomplish that through a technique known as modulation. There may be other things that come along before it. We're not going to talk about those today. But ultimately, to represent that 1 or 0, we need to modulate. Now, how would you modulate? Well, for example, I could tell you that if I say audibly this tone, E, that's a 1. And this tone, E, that's a 0, right? E, 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 I'm modulating. It's pretty bad, but I'm modulating, right? So I'm changing the audio frequency in that case to modulate. So that would be frequency modulation, right? Well, we have the same thing with wireless communications. We can't even do frequency-based modulation, such as LoRaWAN, one of the wireless IoT protocols does. But we could also do amplitude-based modulation. How strong is the signal and how weak is it? We can do phase-based modulation. How is the wave related to the preceding waves and so forth? There are different ways that we can modulate. So we change some characteristic about that radio frequency or electromagnetic wave to represent a 1 or a 0, or a 1 0, or a 0 1, or a 1 1, or a 0 0. So we might be able to represent 4 things and so forth, right? So that's modulation, in some way representing the data on the RF signal. Now, why did I say all that? Because what I want to show you is that it's important to pick the right protocol that allows you to accomplish the range that you need and the rate that you need. So range is about how far away am I from the other device, the two devices that are communicating, and rate is what is the speed of that communication, right? So I have to be able to choose a protocol that gives me the balance of both of those that I need. And in order to achieve higher rates, we need more complex modulation, fancier changes in that radio frequency signal in order to achieve those higher rates. But we also need a very clean signal to be able to hear that well, to demodulate it and be able to understand it. So when I'm at a greater distance, my signal's not as clean, right? It's getting down closer and closer into the noise of the environment. There's much electromagnetic noise in our world, right? So it's getting down closer and closer into that noise. And so for that long range communication, I need a simpler modulation technique. So the simpler it is, the easier it is to modulation with a dirtier signal. And the more complex it is, the harder it is to demodulate it with a dirtier signal. All right. So all that to show you this visual representation of that. So here what we see is a modulation called BPSK. You don't have to worry about it. It stands for binary phase shift keying, but that doesn't matter for our point. The point is, from the left to the right, the signal's getting dirtier, right? So it's getting harder and harder for me to see whether I'm representing that dot on the left or the dot on the right. So look at the first box where it says transmitted symbols. I can either transmit the dot on the left or the dot on the right. By the time the signal has weakened to 20 dB, to the point where the signal is 20 dB stronger than the noise, I should say. By the time that it is weakened to that point, then look at what my dots have become. But I can still tell which one it is, right? And don't worry about what dB and SNR means, by the way, okay? It's weaker, all right? So it's weaker, and I can still tell what it is. But look, a lot weaker still, where it says 6 dB SNR, a lot weaker still, but I can still get that. And in fact, I can 99.5% of the time in actual analysis and tests. if my signal goes all the way down into the noise, it's actually weaker than the noise, then it looks like the far right image. And the reality is, while that looks like to us humans, we couldn't possibly figure it out, you can't actually still demodulate it with some protocols about 58% of the time. Now, let's look at more complex modulation. See, we start out with all these dots. See, the simple modulation, you had 2 dots, right? Now with 64 quadrature amplitude modulation, again, doesn't really matter what that is for this. You see all those dots. Look at how it looks already. At the same weakness level where we could still get 100% of them demodulated with BPSK, we're now down, we've lost 5%. We can only demodulate 95%. And then go further to the right under the 6 dBs in our column, and now we can only demodulate 18%. And then go all the way over to the minus 20 dBSNR, and we can only demodulate 1.5%. Now, that's actually worse than it sounds, because the tests that determined these percentages in a research project we're not retrying if they failed. It's just, I know they're being sent. Am I receiving them? Okay. So 1.5% were received and demodulated without error. But the problem is that the reality is I mean, look at there's 64 dots, right? I mean, that's basically random chance that I'm demodulating it right. It's not really giving me any effective data delivery. And in a real network, there may be retries, which makes that even worse than it looks. So I only showed you this visual representation to help you understand why it's important to pick the right protocol that supports the right modulation to get your data through. Longer range, simpler protocols, simpler modulation with lower data rates. Shorter range, more complex modulation with higher data rates is generally what you can accomplish. But do keep in mind there are other factors too. More complex modulation is more CPU intensive and so forth. So that is a factor as well when it comes to battery life, for example. All right, let's go to our final topic before we go to Q&A, and that's the wireless IoT design framework. So we've talked about the fact that IoT really has evolved out of Industry 4.0 and also the fact that it's beneficial in a lot of different industries and use cases. And we've seen some examples of different protocols. So now, how would we go about building a wireless IoT solution? Well, it's going to start with requirements and architecture. And I don't have the time to go into great details about all of that today. So we'll assume that you're getting good, solid requirements. So you know what your requirements are, the demands on the system, and you have built an architecture. So you're at this point, now that you know your architecture and your requirements, you're ready to design the solution. And we can break this into 4 different components: the network, the data, the apps, and operations. So the network is the thing that allows the IoT end devices to get their data to some destination. The data is the actual processing and management of that data. The apps are the applications that can access it. And then operations is about maintenance and troubleshooting and upgrades and so forth. So when it comes to the network portion of the design, we have to design the wireless IoT network, the wired network, and any supporting services that are needed by this solution. So you've got at least these 3 high-level components. And we're not going to go into all the details today of all these parts and pieces, but you can see for the wireless IoT network, we've got to make decisions about protocols, channels, transmit power, data rates, uniqueness of the different protocols, hardware that supports it. And then we've got the wired network side that we have to deal with as well, and any services that are required. And then for the data, we actually have our IoT data protocols. These are protocols that are designed specifically to deal with IoT data, or maybe they're legacy protocols that are being used for IoT data, like HTTPS that we use on the web. And then we have our data storage, which might be good old-fashioned relational databases, SQL databases, or it could be no SQL databases, real-time processing, all kinds of factors there. And then you have your apps that are going to access all of this data. And then finally, monitoring and maintenance and operations. So if you think about it, this gives you kind of the puzzle pieces to a certain extent that you need to consider to build the network. But there's one very important thing that's not listed here, and that's the cross-cutting planning and design of quality requirements. So quality requirements are cross-cutting. They go across all of these different sectors. And it's very important to keep that in mind. So security needs to be end-to-end, for example. To have really good performance, I can't just have a good wireless IoT network. I need it to be connected to a good wired network. I need the IoT data protocols to be implemented appropriately with the right number of servers and so forth. So end-to-end, I need that if I'm going to have good performance. And the same is true for reliability, durability, availability, et cetera. So these are cross-cutting, and they're your quality requirements being implemented in your design. So let's just take an example of something we might think about here, like data processing. Do we want to do it at the edge, in the fog, or in the cloud? Well, the factor here we need to think about is latency. So latency, in general usage of the term, and there are a lot of variations in how people define this, but it's the time loss allowed between two states. Now, what does this mean? It means that you have one state, and then by a certain time, you have to be in that next state, right? That could be taking action or so forth. For example, the time between a detected problem and a chosen response. So the first state, problem detected. The second state, I have a response. All right. So what is the allowable time loss? Well, we can classify the tasks that we're monitoring and working with in order to determine exactly what that latency allowance is. And so we might have just data that's for long-term use. We're harvesting it only for business insights. We don't need to take any immediate actions. So that stuff could all be in the cloud with no harm, right? But then maybe it's delay tolerant. So we do need to take some actions, but they don't have to happen in milliseconds. They can happen in a second or 2 seconds or something like that, right? So then we might think of the fog or the cloud. And then low latency, now we're probably dealing with the fog only, not ever going out to the internet, fully in the cloud, and in the edge. And then extreme low latency, where I need that sub 10 millisecond response and action, then we're probably going to want to be at the edge. So think, for example, the need to shut down a conveyor belt to save human life, right? So obviously I want that to be extreme low latency. So I'll give you an example of this very rapidly here. And that is a round trip time example, because that's what we're dealing with if we go to the cloud. And so what we're dealing with here is we've got latency in the end device on the far left. That's the actual sensor. 3 milliseconds between the time it senses and the time it sends the information, 2 millisecond delay to send it. Then there's latency in the gateway, 4 milliseconds, we'll say, 15 milliseconds latency communicating to the cellular network, 35 milliseconds traversing across the cellular network, 11 milliseconds from the last hop of the cellular network to the cloud, 8 milliseconds incurred by the cloud processing itself. Then the server in the cloud does its processing and analysis, 37 milliseconds there. And that's just getting it to the server. Now, if I need to know an action I need to take, it's got to go in reverse all the way back. So it's 203 milliseconds in this example. And this is actually a pretty good example of a round trip time going out to a cloud service and back. And there can be better, but there can be far worse. So we have to certainly contemplate the latency demands and make sure we're dealing with those. And one more example, we talked about those cross-cutting factors of quality, one being performance. We just talked about latency. Another is security. And so what we're dealing with here is we've got the attackers. They might be external or internal, and they initiate attacks, right? Eavesdropping, physical damage, replay attacks. And these are just some examples of possible attacks. And the targets of the attacks may be our devices, and they may be our protocols. It may be our data, or it may be our applications. So they threaten all of these. And because of the introduction of IoT and the dependence on IoT that is going to continue to evolve over time, it becomes very, very important that these things continue to be operational. So very quickly, just contemplate, if a person that runs a machine is the only person that can run the machine in your company, and that machine needs to be run every day for at least 2 hours, then you have a high risk there, right? If that person is ill for a period of days, then the machine cannot be run for several days, which could back up everything else. Hence, we do cross training, right? Other people are trained to also be able to run the machine. Well, think about that. That's a simple example. Now you've got 1,000 IoT devices, and your environment just does not work the way it's supposed to work if they're not working. So obviously security becomes key, doesn't it? High risk there when those devices are many and any numbers of them could be a point of attack. So we have to make sure that we have good security in place, and time prevents us from going into great details about all the security solutions available today. So we can wrap it all up and bring it all together by thinking of wireless design as a process of synthesis. We're bringing together different systems or even systems of systems into one huge system of systems, which is what our IoT solution is. IoT solutions most generally and in most cases can be thought of as a system of systems. There are many different systems. The end device itself can be thought of as a system. The wireless IoT network can be thought of as a system. The wired network to which it's connected can be thought of as a system. The data processing servers like our proxy servers, our data protocol servers like MQTT servers, et cetera, can be thought of as a system. Our applications can be a system, and then the whole thing, all of it together, can be thought of as a system of systems. So what we want to do is we want to get the right protocol on the right channels with the right transmit power, and then all of that is going to give us our wireless network and other details as well. So let's just give you an example. And then we have our hardware, the end devices. It has to have the right sensors, communicating at the right data rate, and addressing any uniqueness challenges that our particular solution might introduce. And then, of course, across all of that, we need our quality requirements. And if you have the wrong puzzle piece anywhere, you may not be able to meet those quality requirements, either availability, reliability, performance, security, et cetera. So as you can see, wireless IoT can become a very complex thing. And of course, at CWNP, we have an entire track of training in the wireless IoT world, starting with CWISA and then moving on through CWICP, CWIIP, and CWIDP, all the way ultimately to the CWISE, the elite certification for wireless IoT solutions engineers. And so wireless IoT is big, but it's also very beneficial and very powerful to us. And we're going to see more and more wireless IoT implemented over the next decade. The trends are only toward growth. And so this is a key area of understanding and technology that you want to make sure you're prepared for this next decade. Okay. And with that, I want to first of all say thank you for everyone that has joined us today. And then I think we're going to open it up for question and answer at this point in time. All right, I do see one question in here already. And if you have additional questions, please go ahead and go into the question and answer panel, and you can ask questions there. An individual asks, how can I get hired in an IoT industry? What education, knowledge, experience do I need to qualify? And how do I earn that? That's a very good question. And here's the shocking thing. Until CWNP developed the wireless IoT track that, of course, Sunset Learning Institute can provide training on, there was really no organized learning plan for IoT that went into any depth. And we only lightly cover the wired side of IoT. We don't really get into heavy details there because our focus as a company is on wireless knowledge certifications and wireless skills. And so our primary focus is on the wireless side of things. And yet we have 4 different certifications covering this information, starting out basic with CWISA, basic to intermediate, and then going intermediate to advanced with the others. And so clearly there's a lot of knowledge to gain. And the interesting thing is, when we first introduced this track about 18 to 24 months ago, we received contact from a couple of different colleges that were saying, we need to train people for IoT. Local industries are coming to us saying that we're not providing employees that can work in the IoT space from a technical perspective. And so colleges are struggling to have curriculum that actually will accomplish the goal of industry and what they're looking for. So most of the people that are out there working with IoT today come from 2 backgrounds. Well, 3 if you include cellular, but we'll focus on the other 2 because the majority of the pools come from there. And that is operations technology. They were the people dealing with PLCs, DCS systems, things like this. Basically the old industrial technologies that have been around since the 60s, 70s, 80s, and 90s. And then they started wanting to do wireless, so they started just implementing it themselves and figuring out how it worked along the way. And the other side is people coming from the Wi-Fi space. And they knew Wi-Fi, they knew it very well, and they're learning these other non-Wi-Fi protocols to be able to implement IoT. So that's where the greatest pool of these employees come from. So as far as new learning, I can certainly say to you, in my opinion, and I don't feel this is a bias because I've looked around at all the solutions that are out there, and that is that the CWNP wireless IoT track is sort of the most exhaustive of the training programs that are out there for wireless IoT, going through all 4 of those certifications. There are some colleges, though, that do offer some courses now, and in fact, some of them use our materials for those courses. And you can look around and find some other certifications as well, but there are none that are quite as exhaustive as the ones that we have delivered over the last few years and continue to enhance. In fact, we're updating CWISA, the first one, this year in 2022. The second question is, how can I get started with IoT and what are the certificates needed? Okay, and I think I kind of answered that one on the fly as I was going along with it. Let me say one more thing, though, and that is another thing you can do to get started is to do it on your own, build your own lab. It can be very inexpensive. You can get a Raspberry Pi or an Arduino, either one, and then you can get Grove boards and Grove hats, add-on modules that allow it to function as different wireless IoT protocol types, Zigbee, XBee, LoRaWAN, 6LoWPAN, even Wi-Fi, BLE, etc. So you can get, I recommend a Raspberry Pi because it gives you a lot more flexibility than the Arduino, even though it's a little bit more expensive. You can get 3 or 4 Raspberry Pis and you can build your own wireless IoT networks. You can then plug in sensors, learn how they work. So you can do an awful lot with a Raspberry Pi in the lab. Very, very good way to get started. You can even go beyond that then. And if you want to look at the full stack, you can have a Raspberry Pi with sensors. Then you can get a free AWS account that allows you to do many, many things for free without ever paying any money. But be careful what you do in there, because you can't accidentally start something that can cost you thousands of dollars. But make sure you're using only the free stuff. And then you can even have your IoT devices work with the AWS cloud. Another question has come in from Joe saying, why are you not talking about the other frequencies, 5G and NB-IoT? Well, we do. I had to kind of pick and choose what to get into here for today's webinar. In CWISA, we do talk about cellular, though we talk about it lightly. We made the decision through the process of the development of this track that explaining the details of the internet working of the cellular network were not relevant to our target audience, the people that we were training and helping to have the knowledge and understanding to work with these. They simply needed to know the capabilities of the cellular network so that they could decide whether that was the good solution for them or not. Should I connect my gateway to the cellular network, or should I connect my end devices directly to the cellular network instead of going through my own local gateway? So in other words, is the cellular network just the backhaul, or is it my primary connection point to the cloud or to the enterprise network? So we do talk about it. We have an entire chapter just dedicated to cellular in the study guide and in the CWISA class. We'll see how that gets enhanced or modified in the new version this year, but it is something that is covered there. We simply didn't get into it today for sake of time. So thanks for that question, Joe. Different groups. All right, so let me just say my last part here today, and that is thank you very much, and I'll turn it back over for any closing remarks they may have.
That's all we had here. So thank you all so much for joining us today. Again, look for that email that'll be coming out on Monday, and we hope to see you in class soon.
Excellent. Thank you. And thanks, everyone.
Bye. Take care.